Well, good afternoon and welcome. I am Tarlochan Chima, Software Development Manager for Amazon Cloud Drive Services team, and with me is Ashish Mishra. He's our Senior Developer. And today we will share with you how Amazon Cloud Drive Services is built on top of AWS and how we are able to scale our services to millions of users, hundreds of billions service requests, and terabytes of uploads and downloads at a very high frequencies and low latencies. To give you a quick overview of the topics we will be covering today, we will give you an overview of Amazon Cloud Drive. We will share with you some of the key use cases and some of the challenges around enabling those use cases on the services side more specifically. And then we'll share with you what were some of the key AWS building blocks which we leverage to solve some of our big challenges, and how we integrated different AWS services to build our Amazon Cloud Drive Services architecture. And then Ashish will get deep into some of the key components, like how did we build a very scalable and robust asynchronous pipeline, which enables our content and metadata ingestion. And also, we leverage different AWS data stores. So how do we manage consistency, the data consistency across different AWS data stores? And then finally, we will share with you Amazon Cloud Drive API. This is a new offering we just announced this week. This enables all the developers to build cool applications on top of our services. So before we get started, I just want to get a sense, show of hands, how many people here actually use Amazon Cloud Drive? Few of you. Good. And Amazon Prime Photos? All right, all of you. So let me give you a quick overview for all the other audience here. So Amazon Cloud Drive is a place where you can store any kind of content, photos, videos, documents, any kind of files. And you can access this content from anywhere on the web, or you could use one of our applications. We support different platforms. We have applications for iOS, Android, PCs, Fire OS, if you have Kindles or Fire TV. And then we are also continuing to work to support other platforms. The Mac application will be available in near future. And if you want to learn more about Amazon Cloud Drive, you can go to amazon.com/cloud drive. Let me quickly show you what that looks like on the web. So if you go to amazon.com/cloud drive, it takes you to this page where you can see. Let me bring this here quickly. So this is the page where you can go and you can see the journal information about Amazon Cloud Drive. One thing we recently announced was, if you're an Amazon Prime member, you get unlimited photos, and that's something you see right on the top. And if you go down here, you could find more information, including what are the different kind of plans we offer. And further down, you can find the application you might be interested in. Like I said, we have Fire OS, Android, and iOS. And then also the PC application you can download here. And so let me share with you what were some of the key use cases for Amazon Cloud Drive. One of the big thing our services needed to enable was be able to scale and store any kind of content. So the content comes in a large variety, and it comes in a very high volume, and obviously it comes in a very high velocity. And so the challenge here is, how do you store this content in such a way that it's durable and it's available, as quickly as you upload it. And then we are able to scale to millions of customers at the velocity and volume at which comes. The second one is related to the content. When you get a lot of variety of content, you get variety of metadata as well. And the metadata, with more variety of content, the metadata keeps growing. And the challenge is, what do you use to store this metadata, which continues to grow and changes, and you should be able to provide different ways to get to this metadata so that your clients and application can build some innovative organization and navigation features for your end customers. Another big challenge we had was with the high volume, velocity, and variety of content we get, the content gets uploaded by, say, one device. Maybe you use your camera, you use your PC, you upload this content, but then you want to view this content on your phone and your tablets. And so we wanted to make sure that we give a really good experience on multiple devices. And for this, we wanted to create different formats of previews or thumbnails, depending upon if it's a videos or document or photos, and be able to do that at a very high pace and scale that to terabytes of uploads, which happens at a very rapid pace. Now, the content doesn't just get stored on cloud drive. It is also shared by the customers with their friends and families. They want to experience that content with their friends and families. And so the scaling problem just kind of increases. So you can imagine, like, if you have to kind of build a system where you were supporting for say millions of maybe downloads, but now with the more friends and families which are downloading maybe the same content, you have to scale even further, right? And so the download needed to be optimized further. And then you might have experience in running some of the large-scale services. The key challenge here is, how do you monitor these services proactively in near real time and be able to detect some unusual patterns and then be proactive in taking care of maybe some of the things which may degrade your service's performance, right? So these were some of the big challenges. There were others, but these were by far the biggest challenges we faced. So let's look into how we leveraged AWS to solve these. So the first one, like I said, was we wanted to have a very robust content repository where we can store variety of content with very high velocity and be able to scale. And this is where we use S3. So S3 just works out of the box. There's nothing more we do. And it provides a very highly available, robust, and scalable content repository. We also leverage CloudFront to solve our sharing scenario, where we wanted to scale even further for our download paths. For the metadata storage, there is some known metadata which we understood very well, but then there was metadata which continues to grow as we get variety of content. So we needed again, a very highly scalable, very fast reads and writes, a metadata store, which provided more like a NoSQL document database functionality, but at the same time, it was fast for key value kind of lookups and optimized to do some of the known queries paths. And this is where we leverage DynamoDB. And for more flexible indexing, we leverage Cloud Search. And Cloud Search provides us flexibility in sense where new metadata becomes more known, and now we want to kind of provide query patterns to our clients. Then you just go to Cloud Search and enable the indexing on top, and you're able to kind of provide the needed filtering, sorting, grouping, all kind of advanced query capabilities which are needed. For content ingestion, when the content gets uploaded, Like I mentioned earlier, we create different previews of videos. For this, we use the AWS Elastic Transcoding services to generate different formats so we can support different devices. And for the metadata ingestion, when we write the metadata to DynamoDB, we also push the metadata to Kinesis Stream. And from there, it gets picked up and pushed into different messaging queue where we leverage SQS. And different messaging queues are optimized depending upon what we're trying to do. Like there is a messaging queue which is optimized just for cloud search. Like you need to be smart how you use cloud search. The amount of metadata you want to kind of push to cloud search, you have to kind of batch it appropriately, and then you also have to kind of tweak the frequency at which you push to cloud search to get the best out of cloud search. So there is a messaging queue for that. There's another messaging queue which we use to back up our metadata into S3, and then there is another one which we use for notifications through which different clients and different services integrate to our services. For analytics and monitoring, like we get billions of service calls, and obviously the logs just grow. And this is where we leverage EMR heavily. We process those, and then we push that data into Redshift, which is used heavily for our operational analytics and helps us to get a better sense of our services. And for monitoring all the AWS services, we use CloudWatch heavily. And for deploying and provisioning and managing our EC2 instances, we use CloudFormation very heavily. So let me give you a sense how all this comes together. So as you can see here, S3 is our content repository. The metadata is stored in Dynamo, and we use Elastic Cache to cache some of the more frequent query results, which we know won't change a lot and which are needed for optimizing different paths. And then the asynchronous pipeline is made of Kinesis. When the data gets written to Dynamo, it gets pushed into that stream, and then from there on, we have different messaging queue for Elasticsearch, backing up into S3, and also for doing our notification for letting other services integrate with us. Already talked about cloud search. It provides flexible indexing, full text search, and all kind of advanced queries where you want to kind of group and sort and provide multiple filtering capabilities. And then EMR and Redshift enable our Redshift. And for our management, we heavily use CloudWatch and CloudFormation. So at this point, I'll let Ashish come over and talk more and get deep into our asynchronous pipeline and how we achieve the data consistency. Thank you.
Hi, everyone. My name is Ashish Mishra. I'm an engineer on the CloudDrive team. And as I drill into the architecture a bit, hopefully some of the design patterns will be familiar to you and applicable to your own services. So what problem were we trying to solve? CloudDrive launched about 3 years ago on a largely homegrown set of processing pipelines and databases. Over time, we have scaled out to where we now have tens of petabytes of content. As Darlojan said, we're getting hundreds of millions of service calls per day. And our backends have not scaled to the level that we want without adding a lot of operational overhead. We found we were spending about 80% of our time on monitoring, replacing hosts, checking for performance at a pretty low level. So one of our goals was to be able to scale out to the level that we expect. Now, this growth in traffic pattern is not smooth or predictable. It's very bursty. And we expect over the next year, as we launch more features, more integration with Amazon backends, that this traffic growth will continue. The other aspect of it was our functional requirements keep growing. We are launching the public API. We expect to have a whole new set of requirements from our previous use cases. And we wanted to be able to expand fluidly as time goes by to add more requirements. So a little bit about what we were trying to achieve here. One of our core goals is durability. And this is something we could not compromise on. The customer impact would be somebody uploads their baby photos to Cloud Drive, deletes them from their local device. That's something where we need guarantees as strong as S3 provides. The next one was we need to be able to scale out. And this is a challenge with many of the traditional database systems. Scale out requires either downtime or a huge performance lag for periods of hours. That wasn't acceptable to our customer base. We want core operations to have a very high availability and low latency and very consistent performance. This is not something that extends to queries. So queries might be, show me all my files that were uploaded in 2013, show me all the files in this folder that are ordered by name, or show me all my uploads which have a certain string in them, like reinvent. Here we can accept eventual consistency. We don't need strong read your writes consistency. But we do want to have near real-time updates of queries. So we cannot take batch processing, which takes an hour to update. The other aspect of queries is our requirements are all over the board. We have requirements for strong filtering, like very precise filtering. We have requirements for particular ordering. Some of our queries populate UX, like in the website Tarlochan just showed you. Some of our queries are for backend business metrics, for analytics, monitoring. And there we can have kind of higher latency, but the queries are much more heavyweight. And finally, we have some custom requirements as we scale out the third-party API. We're going to have developers come in with query requirements and aggregations that are really specific to their application. So Shiva had a great visual in his previous presentation with a relational database as this mutant Swiss Army knife. And we know that model doesn't work. We have specific backends that are optimized for particular use cases that they handle best. So when dealing with these backends, we adopted kind of a hybrid Lambda architecture. And I'll explain why I say hybrid in a few minutes. But the main concept is you have a central replication stream of updates, and all your backends are reading out of the same stream. So what backends am I describing? Well, key components of the architecture. We have a highly resilient, durable content store. Content here is the actual payload of the files. It might be the bytes of your PDF and so forth. We have a primary metadata store, and this is the authoritative source of information about uploaded metadata. Metadata would be extracted EXIF information from your photographs. It might be like OCR text from your PDFs. The size of the metadata is maybe an order of magnitude to 3 orders of magnitude smaller than content. We have query planes, which are secondary stores. And this gets into what I said before, where different backends are optimized for different use cases and handle them really well. Tying them together, we have a central replication stream, which populates these query backends. And finally, we have replication workflows, which transform the data as needed. So you may do filtering, you may do adaptation to a different schema for your particular backend you're writing to. So if we look at these building blocks, these roles are pretty well filled by platforms that are provided by AWS. For content store, you have S3. It's extremely resilient to 9 nines or more. For the primary metadata plane, you have DynamoDB. And this gives you extremely predictable performance, and it's extremely fast for individual reads and writes. You have a limited degree of queryability with secondary indexes, local and global. For richer query functionality, you have multiple choices. One of them is cloud search, and this gives you full text search. It's going to give you indexing, and to some degree, it's going to give you like sorting and pagination ability. For more heavyweight aggregation, you have Amazon Redshift. This gives you essentially data warehouse query capabilities. You could do something like, well, what is the 90th percentile of customer corpuses across all of the millions of files, all the millions of customers and billions of files in our database. For the replication stream, we have Kinesis. This is a durable, resilient stream. It's going to give you the ability via sharding to scale out horizontally to an essentially unlimited degree. And finally, for our replication workflows, here you have a couple of options. For our architecture, our use case has very simple transformations. They're relatively self-contained. So SQS is a good, lightweight model for this, where each SQS message corresponds to the state of your workflow. If you're doing more complex mapper, reducer, multi-step workflows, perhaps you want to leverage some of the more heavyweight options given by AWS, like SWF. How does this all tie together? So there's a lot of information on this diagram. I'm going to go roughly counterclockwise as I describe like a day in the life of an uploaded node. Users call APIs in Cloud Drive service to perform their CRUD operations. For all writes, we publish a notification message to Kinesis, and we subsequently write to the DynamoDB table. And this ordering is important. If the Kinesis publish fails, then the entire transaction is rejected. However, if the Kinesis write fails, we may still get throttled or have like loss of availability of DynamoDB, and we'll come back and validate our data against DynamoDB later in the pipeline. The contents of the record are the primary key, which is the hash key and range key in DynamoDB, and a version number, which I'll describe in some more detail in a little while. Reading off of the Kinesis stream, you have multiple consumers. You could have special case consumers that do, split off by customers and have per customer processing. You can have notifications to an external system like SNS. You can also have kind of an incremental backup that reads out chunks of updates and saves them essentially as a write-ahead log. And to populate the backends, we have replication resilient workflows that use SQS to model the state of the workflow. What SQS buys us, it gives us kind of back off and retry semantics. You could have a worker fail, the message stays in SQS. You can have the desire to back off, and this is implemented by extending the visibility timeout in SQS. One consumer of these workflows would be writing to Cloud Search, and we can read out batches of messages from SQS because it's more efficient to publish to Cloud Search in that mode. The workers, as I said, come back and validate the information against DynamoDB. So this is where we slightly deviate from a pure Lambda architecture in that the stream is not the authoritative source. DynamoDB, our primary metadata table, is the authoritative source. If you're building this out in the next year or the next few months, you have another option, which is to use DynamoDB update streams in place of the Kinesis stream. Yes? This is purely the metadata pipeline. I'll describe how content gets to S3 shortly. Finally, in the query path, we have logic to merge the query results from Cloud Search or whatever our query backend is, along with a small set of recent updates from DynamoDB. And the reason for doing this is you have a certain degree of lag in your pipeline. You also may have a certain degree of lag between publishing results to your backend and having them available in the index. And so to override this lag based on your use case, you can get a small set of unfiltered results from DynamoDB, just for a small window of time, merge them in memory with the larger set of query results which you've gotten from your batch processing. A little bit about our metadata model. This is extremely simple, and this is by design. The core notion of an atom in Cloud Drive is a node, which could represent a file, a single file, or it could represent a collection, or it could represent other units of metadata, which we call assets. The node is identified by a customer and a node ID. Within the DynamoDB table, we have a single GSI, which is on the last modified date. The last modified date is the epoch milliseconds. And we cannot use this really as a strictly increasing counter because of clock skew and other issues with using the timestamp. But we can use it as an approximation to get, say, within a certain amount of window, say 5 minutes, we can guarantee that our clock skew was not varying by more than 20 seconds. Then you have the additional attributes, which correspond to the obvious metadata you expect to see for uploads to Cloud Drive. You have the kind, the type of the node. You have a list of parents. Parents are essentially upward pointers to the collections containing that node. And the reason for keeping upward rather than downward pointers is we can bound the number of upward pointers for a node. In the sense that from a customer perspective, you would not have like 100,000 tags on a single photograph. The set of downward pointers cannot be bounded. You could have arbitrarily large collections. So instead of keeping downward pointers, we save the upward pointers. That way we can guarantee that the record is bounded in size. And we rely on our index backends to maintain the reverse relationship. You have name, status, and you have additional content metadata, which may be like the MD5 or the SHA-256 of the uploaded content. It's going to be perhaps for photos, it's going to be like image, EXIF metadata. For documents, it might be other extracted information. So the most common concern is consistency. One of two reasons that people generally push back on having multiple backends. One is query lag, which I addressed before. We can handle that by merging recent updates within a fixed bounded window from the authoritative store. The other concern people have is consistency. How do you know that your separate backends have consistent data, and isn't the store going to diverge over time because of code bugs, data corruption, etc.? So our guarantee around this is, number one, row-level atomic operations, which DynamoDB gives us, and most of the backends we care about or would leverage heavily. For example, Redis, MySQL, Cloud Search, Redshift, all have row-level atomicity of your updates. And this is good enough for our use case, for in Cloud Drive, where you do not require, typically, consistency between multiple file operations, because files are handled independently. This also lets us scale out by parallelizing operations across different files. Now, you do have some requirements of consistency between a file and its immediate parent, but beyond that, we don't need multi-row transactions at a really high level. Within a row, you have a per row revision number. And the guarantee here is that this increases monotonically as the row gets updated. And we enforce this in DynamoDB via conditional puts. We can also enforce this in our other backends. I'll discuss this shortly. Deletes are not tracked as deleting the row entirely, but they're simply a status update. And they also involve incrementing the version number on the row. So they are essentially metadata updates, even though the UX built off of these is going to be different, obviously. At every layer of our architecture, this revision number determines precedence. If you have two versions of the same row, you can always know which is the authoritative one by looking at the higher revision number. So this protects us against most of the edge cases that we're concerned about for consistency. So the three that could arise as a result of your distributed pipeline. Number one, out-of-order updates, where your primary data store gets, perhaps you recycle a file and then restore it. And within your distributed pipeline, those could get merged and applied out of order. We have a canonical sense of the most recent update, which is going to be the version number of the row. Missed updates, these are handled by all of our replication to backends goes into resilient workflows. In the case of Cloud Search, as I showed you, it was SQS. Any individual worker could die or die multiple times. The message will stay in SQS and only be removed once the update has been successfully written to Cloud Search. Similarly, every backend has a resilient workflow that could fail arbitrarily a number of times. We can add exponential backoff, but eventually the update will be propagated. And finally, you have spurious updates, where the concern is that a change may not have been accepted by your primary store for whatever reason, but it still goes through your pipeline and ends up in one of the secondary backends. And the resolution to this is we always come back to our primary store. And once again, we can use the revision number to know whether what's in the primary store should supersede what's in the secondary backend. We have the merge logic to combine results here. A little bit more about some of the backends we've used. I mentioned Cloud Search before. This is fully hosted. It scales out with minimal manual intervention needed on our part. We are able to scale out across multiple domains because we can effectively shard by customer ID and assume that the query traffic against Cloud Search is going to be within the scope of a single customer. Within the scope, it gives us full text search. In addition, it gives us the ability to compose indexes arbitrarily, to have nested Boolean queries, which we could not get directly from our DynamoDB table. Amazon Redshift is great at handling larger level aggregations across the scope of our entire corpus, which could be like tens of billions of rows. So we use it for business metrics, for engineering decisions around scaling. Within Redshift, we have two levels of tables. One is databases for the service logs, which is essentially Flux information. So an example would be, well, what volume of uploads did we see from this particular device in the last 2 weeks? The other one is going to be current state of our metadata corpus. And this would handle queries like, well, how much storage are we using in S3 for current version of PDFs? How much traffic or how much files were uploaded by a given application ID? One key for updates to Redshift, because the primary key is not guaranteed unique. When we update the metadata store, we use a staging table to perform upserts. And as before, we use the revision number to guarantee that the staging table will override the target table if and only if the version in the staging table is higher. So this allows us at any given point of time to have a near real-time stream of updates to go to our Redshift metadata table. And the only constraint here is how large we want the batches to be for efficiency. Additional query layers. A bunch of our services have specific requirements around caching of data in memory. And an example is our photo service, which has particular media-specific queries that it wants to run. And this is handled by having listeners, the same level as the ones populating Redshift and Cloud Search, also can populate these in-memory app caches. If you can handle or if you can accept an extra network round trip, Elasticache is a great solution for in-memory caches. In our case, the size of the caches happens to be fairly small, so we actually keep them on the application service itself. You have additional DynamoDB tables. And this is very similar to having a GSI. The difference being in this architecture, you're no longer bounded by the limit of 5 GSIs. The reason you might want to use DynamoDB is specific of our use cases that have very strong requirements around latency. And an example would be population of a UX from a particular query. In this case, DynamoDB meets this need well because the performance of queries is extremely predictable, it's linear, and the cost is also extremely predictable. It's more expensive, of course, and it is not flexible, but we can handle that by adding additional DynamoDB tables. Finally, we have additional query layers, all of which follow the same design pattern. And as we kind of build out our REST API, as I mentioned, we expect to add more backends. And we have the flexibility to add these and scale them out without affecting, say, our UX that is listening to DynamoDB or any CRUD operations which are accessing the primary metadata table. A little bit about our content download and upload path, really. As mentioned, we have S3 as the primary backend. And to handle one-off stream processing, a common requirement would be like cutting thumbnails for a particular size. And for this kind of stream processing, we have a proxy layer that sits in front of the S3 and streams all uploads and downloads through it. This proxy layer is essentially a stateless client to the Cloud Drive service that I showed in the previous diagram. It's not inherently different from any other third-party client. It doesn't have to keep its own metadata store or any kind of long-lived workflows. It simply writes those back to the metadata as an update, and it's subsequently handled for indexing and so forth in Cloud Drive service. What did we learn going through this exercise? We had huge benefits from offloading our operational workload to these AWS platforms. Going from kind of a hosted database to DynamoDB has cut down our overhead for the core metadata store by about 90%. There is a flip side, of course, which is as you add more moving pieces, this is not a function of moving to a particular architecture, but as your requirements grow, if you add more pieces, there is overhead to support and keep track of outages in these different pieces. So you do need to add in integration testing at every step in the pipeline, and in most cases for multiple steps. For example, one level of integration testing would be CRUD operations being written into DynamoDB. Another one would be downstream workers picking up those updates from the pipeline. And of course, those workers writing updates to whatever backend that they choose. Avoid cascading failures in your dependencies. As you add more dependencies, you don't want kind of an outage, kind of a temporary outage in one to break functionality all the way through your system. And the mitigation around this really is to have fan out to your dependencies at the top layer. Don't create long chains of dependencies. As long as you have fan out at the top layer, a failure in any one component is really only going to impact the particular use case that's reading out of that component. This also gives us decoupling from, say, Redshift with our primary website. Finally, data consistency. A big win for us was being able to have granularity of our guarantees around consistency. What I mean by that is we did not need to build out kind of transactions that span like hundreds or thousands of rows. The benefit to that is, number one, performance, of course, but also scale out. We can really efficiently parallelize operations across rows. Even within a row, using optimistic version checks, we don't need to have forced locks or mutexes across our distributed system. So if you can break down your data model such that your consistency guarantees are self-contained, then you can build out sort of a kind of incremental sequential system for revisions, similar to how we did, without having to couple these revision sequences across like a whole bunch of different rows. That's about it for my discussion of the architecture. One of the big use cases that we were trying to support has been building out a REST API for third-party developers to use. And they can run queries, they can make service calls against these backends that I described here. And a little bit more about the REST API, I'll turn it over to Tarlochan.
Thank you, Ashish. So as I mentioned earlier, this week we announced Amazon Cloud Drive API. This is a REST-based API, which you all can leverage and build new apps on top of Cloud Drive services. You could integrate this API with your existing apps and serve millions of Amazon customers. Here's a link, a little bit long, where you can find more experience, and I think one paper was passed to you guys where you can find more information about this. We also have a booth where you can come and visit us if you want to learn more about this API. So just a few call for action for you guys. If you haven't already tried Amazon Cloud Drive, please do so. If you're an Amazon Prime member, try Amazon Prime Photos. Gives you unlimited photo storage. And if you're a developer, build some cool apps on top of our services. And please do give us your feedback. Thank you again for attending this session.